Alright, hello Algebra 2 students. Today we are going to continue our discussions with systems of equations, but we're going to be looking at a different method. I do not have my normal microphone, so I apologize for the poor audio quality of this video, but anyway, let's move on. Our objective, and I'm not certain what day this will be for at this point in time. I anticipate these notes being for Wednesday's class. Our objective will be the student will learn to solve systems of equations by the elimination method. If I am correct and these notes are for Wednesday's class, that would be November the 6th. As always, anytime you need more time to copy your notes, press pause and then hit play when you're ready to move on. Now what you're going to see with the elimination method is just like with substitution. We're going to have a series of steps that we're going to need to memorize. But before we get to that, let's look at a property that all equations have. Okay, on my notes there it says look at properties that all lines have, but it's actually a property for any equation. And what we're going to examine here for a moment is if we were to take an equation and multiply the whole equation by some value, would that equation be changed? In other words, if you multiply an entire equation by some value, does that actually give you a different graph than the one you would have had in the first place? Now, common sense would tell us that if you change the equation, that you are also changing the graph. But let's look a little bit deeper. If we were just to take a basic equation like a linear equation, okay, in this case we're looking at y equals 3x plus 2. And we were to graph it, of course we would have a y-intercept at 2 and a slope of 3 over 1, up 3 over 1. Now the question is, theoretically, what would happen if we took this equation and we multiplied it by any number that we can think of? And I just picked on -7 for no particular reason, but let's have a look and see what happens. If we take y equals 3x plus 2 and we multiply it by the -7 that we just talked about, what we would end up with is -7y equals -21x minus 14. Now if we were to take this equation and again solve for y, which would involve dividing the entire equation by -7 so that we could isolate y again, look what happens. We end up with the original equation before we messed with it, y equals 3x plus 2. And since we ended up with the same equation, that of course means we will end up with the same graph. So the short explanation of that will be that yes, we can take any equation that we want and we can multiply it by any value that we want without changing what the equation means. This is going to be a cornerstone property of the elimination method. Okay, now the elimination method focuses on removing a variable from an equation by combining the two equations of the system in a way that is very similar to what we were doing with the substitution method, but the way that we were removing a variable with the substitution method was by way of substituting values into other equations. This one is going to try to remove the variable by actually combining the two equations as they're written. Okay, so we have step-by-step process for solving by elimination. The first step is to look at the equations, and we're hoping to find a variable, okay, either the x's or the y's, and we want those x's or y's to have coefficients in common but with different signs. Meaning, maybe you have 2x's in one equation and -2x's in the other equation. 5y's in one equation, or -5y's in the other equation. Okay? If we can find this condition existing in the problem already, this makes the elimination method very easy and very short, and we can skip over a lot of the steps. So if we find that condition, we can skip all the way to step number 4. If you do not have this condition, but you still need to use the elimination method, then we're going to proceed on to step 2. Now, step 2 is going to be to figure out what the equations could be multiplied by in order to get what step 1 was looking for. This may involve just multiplying one equation by some value to make the coefficients match up the way step 1 wanted, or it might actually mean picking one value to multiply one of the equations by and a different value to multiply the second equation by. You'll get the hang of this more when you see some examples. Now, once you figure out what those equations could or need to be multiplied by in order to get that matching coefficient with different signs that step 1 talked about, you do the multiplication, multiply the equations by whatever it is you decided they needed to be multiplied by, and you write down your new equations. Then you go back and you look at step 1. Look for a variable that has coefficients in common but with different signs. If you have done steps 2 and 3 right, you will have this condition. Then you can go on to step 4. If for some reason you did not find the coefficients in common but with different signs, that means we did something wrong in steps 2 or 3 and we need to try again. Now, assuming we can finally get past step 1, okay, then what we're going to do is we're going to add the two equations together. This will give us a new third equation, and this new third equation will have lost one of its variables. You're going to write this equation down. It is going to be how we're going to move forward. In step 5, as I said, from step 4, there will only be one variable left. We will solve this new equation for whatever variable is left. That will give us half of our answer. We will take this answer, that half of that solution, we will substitute it back into the original system, and you can pick on either equation that you would like. When you plug in that value, you will now only have one variable remaining. It will be the variable that you have not yet solved for. When you solve step 6, you will have your solution. Your ordered pair will be the solution for the system. Okay, now let's see this work in a problem. Here is a system of equations. We have x plus y equals 5. We have 3x minus y equals 7. Okay, so let's walk through our steps. Step 1 said to look for a variable that has coefficients in common but with different signs. Well, take a look at the x's. You have a positive 1x, you have a positive 3x. We can make elimination work with the x's if we need to by multiplying the top equation by -3. But before we do that, let's look at the y's and see if maybe they might be a little bit better. The top equation has a positive 1y, the bottom equation has a negative 1y. Okay, we have a variable that has coefficients in common. They both have a 1, but with different signs. One of them is positive, one of them is negative. Okay, so this is good. Our coefficients of y are set up nicely for the elimination method. Our y's have coefficients of positive 1 and negative 1. Since we have found what step 1 wanted, we get to skip to step 4. Step 4 tells us to add the two equations together to get a new third equation and write it down. Okay, so we're going to add our two equations together. You have 1x plus 3x's. That will be 4x's. We have a positive 1y. We have a negative 1y. When we add these two equations together, that will give us 0 y's. And then on the right side, we have 5 plus 7. That is 12. Our new equation is 4x equals 12. Okay. Now step 5 tells us that we should take this equation that we just figured out, 4x equals 12, and we should solve for whatever variable is in it. Obviously it is x. We have 4 x's, but we don't want 4, we only want 1. So we will divide both sides by 4, and that will give us x equals 3. Step 6 tells us now take this value and take it back to the original system and plug into either original equation, and you solve for whatever is left. Well, it does not matter which equation you use. Okay, so you have free reign to pick either one of them. Usually what ends up happening is one of them will simply look nicer to deal with than the other. So go ahead and pick that one if you choose, but you can pick either one. Okay, so the x plus y equals 5 equation, that looked pretty good to me. So I'm going to take the x out of the equation and instead plug in a 3, because we now think x equals 3. Now we have an equation that only has y in it, so we solve for our y. Obviously we need to subtract 3 from both sides to isolate y, and y will equal 5 minus 3, which of course is 2. You now have an abscissa in step 5, you have an ordinate in step 6. When you put them together, you have a solution. Our system will intersect at -3, 2. Now obviously this one was nice because we had a variable that was already set up. We did not have to do steps 2 and 3. Let's look at a system that will make us do steps 2 and 3. Solve the system of equations. X plus 3y equals -2, and 2x minus 4y equals 0. Okay, so step 1 tells us to look for a variable that has coefficients in common but with different signs. Okay, we'll look at the x's. We have 1x in the first equation, 2x's in the second equation. That's not what step 1 wants, so let's look at the y's. We have 3y's in equation 1. We have -4y's in equation 2. That is not what step 1 wants either. Okay, so what we're going to need to do is we are going to need to figure out, okay, what could the equations be multiplied by in order to get what step 1 wants. Now it does not matter. You can pick on the x's, you can pick on the y's. I think in this case it would probably be a little bit easier to get the x's. And the reason I think the x's would be easier is because when you look at the y's, okay, it's going to be difficult. We cannot multiply, well we can, okay, we can't multiply the top equation by a simple number to make the 3y's become 4y's. Okay, in the second equation, we can't think of a simple number that we could multiply the -4y's by to become 3y's. So it seems pretty clear to get the y's, we're probably going to have to adjust both equations. However, I think the x's, we can get away with just multiplying one of the equations. Okay, I think the x's would be easier because we can pretty easily get that top equation to give us a -2x. And that would match up with the +2x in the second equation. Okay? So we're going to multiply, in this case, we're going to take that first equation and we're going to multiply it by -2. Step 3 says to actually do this multiplication and write down your new equations. And then try step 1 again. Okay? So if we multiply the first equation by -2, and leave the second equation alone, we will get this. We get a -2x minus 6y equals 4. We left the second equation alone. Now that we think we have this, we're sent back to step 1. Look for a variable that has coefficients in common but with different signs. We believe we now have it, -2x and +2x. So we can go on to step 4. Step 4 said to add the two equations together to get a new third equation and write it down. Okay? So when we add our two equations together, what do we end up with? Negative 2x's plus 2x's, that will be 0x's. That's good. That's what we wanted to happen. One of the variables to be eliminated. And then we have negative 6y plus negative 4y. That's negative 10y's. And 4 plus 0 is, of course, 4. Okay, the fifth step said to solve for the variable in the third equation. Obviously, we have negative 10y's, but we do not want negative 10 of them. We want positive 1. So we're going to divide both sides of the equation by negative 10. And that will give us a value of y equals 4 over 10 reduces nicely to 2/5, and a positive divided by a negative is always negative. Okay, so our y value is negative 2/5. Step 6 tells us to substitute this value back into either original equation and then solve for the remaining variable. Okay, again, you can pick either equation that you want. I have selected the x plus 3y equals negative 2. We plug in the y value. We have x plus 3 times negative 2/5 equals negative 2. Okay, remember there in the center, to multiply two fractions together, we simply go straight across the numerators, straight across the denominators, and that will give us negative 6 in the numerator, 5 in the denominator. Now we just need to isolate our x. That will mean adding 6/5 to both sides of the problem. On the right side, we will need common denominators. Seems pretty clear that we have that negative 2 over 1. If we multiply the numerator and the denominator by 5, that would give us negative 10 over 5. And when we add them together, that gives you negative 4 over 5. We already had an ordinate from step 5. Now we have an abscissa in step 6 to go with it. So when we put them together, we have an ordered pair. The system intersects at negative 4/5, comma, negative 2/5. Yes, it is possible you will end up with fractions. These systems do not always cross at whole numbers. Fractions are just part of math. Let's just get used to it. Okay, I have one more system, and I would like you to give it a try. We will go over it in class whenever we do these notes, and again, I think this will be for Wednesday. But have a look at this system. 3x plus 2y equals 23. Negative 2x plus 3y equals 2. Go through your steps, read them one at a time. I think what you're going to find in this case is that there is not a variable that is particularly very easy to get to. This one was going to involve having to multiply our first equation by something and multiply our second equation by something to get a step 1 that will actually work. Just to give you a little bit of hint, I would probably be looking at the x's. So see what you can do to make the x's become a coefficient that could be in common for both. Sorry the notes are a little long this time. Sometimes with these methods it takes several steps. It takes a little time to go through it. Anyway, I appreciate you getting all the way through your notes. We'll see you in class with these notes, I believe, on Wednesday.